Okay, thank you for everybody for being here. So this is the topic of this talk is something which has been done for some people, actually one people sitting in the audience, one person sitting in the audience, and a few people from an ex-PhD student, which is probably the workforce behind this topic here. So the talk is divided into two main parts. So the first part I will discuss something related to measurement-induced phase transition, which I will briefly give an intro to, and in particular we'll discuss the impact of imperfect detection, so some problem with your not ideal detectors on measurement-induced phase transitions. And the second part, I will discuss something really closely related to measurement, to monitored system, but in a so-called minimal model, which I will discuss later on. So what is phase transition in general? So just to introduce the idea of monitored phase transitions. So you know what term of phase transition, of course, that happens at equilibrium, and a second type of transitions, very quite not notorious one, is the so-called quantum phase transition, which happens at zero temperature, and it's related to some quantum degrees of freedom, which is changing, and due to some quantum fluctuations, we can see an abrupt change from the ground state of the system to another ground state of the system across a very special point called a quantum critical point. But there is a third class of stuff. So both of these two types of phase transition goes into the so-called domain of equilibrium phase transition, because they happen either at zero or at temperature, a finite temperature, but are in an equilibrium with some environment. A different story is when you start looking to situation where you sit on an equilibrium which is dynamical due to some external drive and possibly the presence of some loss. So in between the so-called equilibrium system and let's say open system or non-equilibrium quantum systems, there is a type of phase transition that I will discuss now. So again, what is in a quantum domain? What is a closed system and a quantum phase transition? Essentially, is defined by the fact that you have some eigenstates and the ground state of the system, which for some reason gets closer and closer as the thermodynamical limit, as we go closer to the thermodynamic limit, and we see that at a very specific value in some parameter of your Hamiltonian, these two ground state and excited states basically becomes degenerate. That's the standard view of closed quantum phase transition. In open quantum systems, on the other hand, as I said, we have some external drive, we have a reservoir, we have a quantum system in contact with both of these two things, and the system, the most simple situation is described by the Allen-Bladian. And you can frame in a similar, in an analogous way to closed system, also the phase transition in open systems by looking at the stable state of your quantum systems and start looking at spatial situation in which your stable state changes abruptly because the Lagrangian of your system is dependent on some parameters, and these parameters is slightly changed, and for some reason the stable state gets changed abruptly. So that would be the so-called non-equilibrium quantum phase transition. Something in between is the so-called monitored. We have monitored system where the system itself is quantum, but it may be driven and contact with reservoir if you want, but the essential ingredient is that the system is now continuously observed or stroboscopically observed by some external agent. And in this type of situation, we can again observe an interesting feature if we have a many-body system which is interacting with this type of monitoring. So how would you describe it in a standard quantum information setting? This type.
Fundamentally, measuring is like having a monitor system is like having an open quantum system. Fundamentally,
to some extent, not quite, but only to some extent. That's true in a sense that is true, unless, and now that's what I'm going to do now. I'm going to make this parallel now. So again, if you want to describe in the most elementary way the interaction with a measurement apparatus, you will, in quantum information language, you will resort to the Krauss representation, an POVM, and so forth, or if you want, just a projector. And every time step of your monitoring systems, the system gets updated by the information that you gained after the measurement, right? That's the standard approach. Again, but to make contact with what Francesco was saying, if you throw away the information about the measurement result, so you basically have to average over all possible results, and the effect of this measurement apparatus is a total equivalent to an open system, essentially. So whenever you are completely ignorant about the result. So being ignorant about the result is equivalent to having a system which is an open system evolving. So here the real difference with what we are talking about is the awareness of the result. So that changes a lot. When we talk about measurement and open system type of system. So monitored and open. So there are, again, in the standard Lindbladian formalism, if you want to make contact with the Krauss representation of a Lindbladian evolution, you can express every single click event of your measurement apparatus as a Krauss operator, which is linear in the square root of the time dt that you are interspace every single measurement observation. And that's a very special type of measurement event, which is called click event. If you don't observe any click in a given amount of time, you will evolve your system according to a Krauss operator, which is called the no-click Krauss operator, which is not equivalent to doing nothing. There is a slightly renormalization of what you have to do in your Krauss operator to take into account the renormalization of your state. And this slight renormalization terms is what is called the measurement back action. Sorry. So now, again, to go back into the story of an open system, having an open system meaning throwing away this information. And basically, if you do that, you go back into the full Lindbladian evolution. And this way of describing the Lindbladian evolution in terms of measurement outcome goes also into the name of unraveling of a master equation. Means basically that you assume to have a collection of results, and each collection of results basically gives you a so-called trajectory. Okay, so the collection of results that you get in every single step in time. So the collection of the trajectory, if you sum up all the possible trajectory at the end of your evolution, is the result of the open evolution of the Lindbladian evolution. That's the standard unraveling of master equation point of view. Now, again, there's a special type of trajectory, which is the one in which you never observe a single click, which is called the no-click trajectory. Okay? This plays a special role in this type of setting. Now, when that applies to any type of monitored system, but when we deal with a many-body system, then we can do something more interesting. So, and start looking at what happens if we start looking at every single side of let's say, a many-body chain Hamiltonian. And to tell a long story short, basically, I'll tell you, I'll go a little bit more in detail. So one of the basic ingredients that people have been looking when studying this type of system is to look at the entanglement properties of these many-body systems under monitoring. And the typical quantity that people look is the entanglement entropy defined in the usual way. So now, a key point to have a look to distinguish in this situation is to distinguish between two basic quantities. One is the entanglement and the entropy, the entanglement entropy associated to the to every single trajectory, and then averaging the over every single trajectory. So you do the averaging of the entanglement entropy of every single trajectory. A totally different story is to do first the averaging and then calculating the entanglement entropy. So these two quantities are definitely different from each other because this quantity will basically quantify the entanglement entropy of the open evolution. On the other hand, this quantity will quantify the entropy, the entanglement entropy of every single trajectory, assuming that you can distinguish them because you are measuring them, and then making an average of this entanglement entropy. These two things are different. Why they are different? Because the entanglement entropy is a nonlinear function of the operator. So, what is the main point? The main point is that most of the interesting stories that I will tell you relates to open system evolution, where the steady state is basically a featureless steady state. So basically, most of the time, when you keep on measuring a system, most of the time at the end, and you don't record the result, at the end you get basically an infinite temperature eigenstate, an infinite temperature steady state. So basically, it's totally useless in terms of what you expect from this system. So, so to tell a long story short, the things becomes interesting when you look at this quantity here, and there is a specific value of the monitoring rate, in which you have, across which you can distinguish two different types of behavior. One behavior in which the entanglement entropy behaves as it should in a logarithmic with a logarithmic scaling, also known in this one-dimensional system, can also be called a volume law scaling, meaning that system of if you look at a single, if you don't measure at all, let's say, if you don't measure at all, these type of systems are extremely interacting. So you're assuming, for example, to have a next neighbor interaction, and the ground state is usually very entangled. So it has a volume law entanglement. If you keep on measuring the system a lot, you are basically localizing a lot the system, and then you are destroying the entanglement, at least to some degree, and you end up in a phase where the entanglement has area law, so it's basically short range. So what is the interesting in this type of setting is that
results for local measurements. Right?
that's local measurement repeated everywhere, every single point. Okay, that's the standard setting. So the point is that this happens abruptly. So if you go into the thermodynamic limit, you don't go slowly from logarithm to area law. You go abruptly from volume law to area law. So this is a true phase transition in this sense. So again, so these are the expected way. Sorry, gamma is a generic parameter that tells you how strongly you are measuring your system. So I haven't specified. The rate at least. Yeah, if you do it stroboscopically, would be the rate. If you do it continuously, would be the strength to which the system is coupled to your monitoring device. So the first part. Now, this is the standard story of measurement-induced phase transition. Now, the point that I want to make is what happens if your all this story is told under the assumption that you have a perfect device, perfect measuring device. So you can distinguish every single measurement with 100% probability. So now the question that we wanted to ask is, what if your measuring device is kind of doesn't distinguish some of your measurements, so basically is not very efficient. So what is the fate of the phase transition? Can you really see the phase transition? Is there a trade-off under which you can see or not the phase transition? That's basically I will ask in the negative in a little bit. So how do you model this type of behavior? Basically, the idea is, suppose you have a set of measurements, and if you have a perfect device, you can say you have a measurement, I have no measurement, and so forth. So if you have a bad detector, maybe with some probability, given one where Q is a sort of a detector efficiency parameter, with some probability you miss your click. So basically you're saying I had no click whenever truly you had one click here. So that basically gives you a false negative of your result. So then, mathematically speaking, what do? You start with your unconditioned, your conditioned state that you had if you have no click at all, which is the true phase. With probability Q, you would describe, if you have no click, you would describe your system with this conditioned state. But with the 1 minus Q probability, if your device has an efficiency of Q, you somehow you don't know whether at some point you had a click or not. So your best description of your state is not this one, but it's something in between. So it's basically a totally unknown result. So that means that your next update of your state is not what you would have in a perfect measurement, but it's something which mixes up and which quantifies, this Q quantifies your unknown, your ignorance about the result. So if you keep on use this approach and go in the continued limit, you basically have to change your standard description of your time evolution. Instead of using a true Lindbladian evolution, you have to modify your Lindbladian evolution according to this Q parameter. And what you end up with is this slightly tilted Lindbladian Hamiltonian, Lindbladian operator, which has these two limits. As I said before, Q equals to 0. Q equal to 0. So Q equals to 1 is an evolution in which your device is perfect, and you know with certainty that you have no click at all during your evolution. Instead, in the extremal limit, where Q is equal to 0, you are completely ignorant, meaning that your true evolution is a full Lindbladian evolution. You are basically throwing away every single result.
For non-zero Q, this is still
Sorry?
For non-zero Q, this is a well-defined Lindblad equation.
No, it's not. It's not traceless. Okay. So it doesn't give you. It's not trace preserving. So it's not a Lindbladian.
What about positivity?
It is positive, but it's not trace preserving.
Is it not? Doesn't that term ensure the non-linear term, so that expected value?
Oh, okay. Yes, actually, there's a trade-off. Either you make it trace preserving, and then by adding this term, sorry, I correct that. So either you add this term so that your evolution remains trace preserving, but if you add this term, it is not anymore completely positive. Okay. So it's a trade-off between these two points. That can give you unphysical results, but among your unphysical results, you can get you have for sure physical results as well. So you have to filter among different possible results.
But Q equals 1 is there are no clicks at all, or it's randomized results?
Q equals 1 means that you have never clicks at all. So you are following a deterministic. You are following a deterministic evolution.
So there is no measure.
No, actually, no. It is still positive. No, it is still positive. It is completely positive. Why it is not?
Q is equal to 1, and you have the average last term, right?
Yeah. Because this is a mixture of. It is the mixture of alternating situation in which you evolve the system with no click. You can think of this evolution as a mixture of evolution having for sure no clicks, so deterministic, which is positive. It's a positive defined evolution. It's a completely positive evolution. And on top of this, you alternate evolution with a complete invariant, which is again completely positive. So this is completely positive. Still. Anyway.
But for Q equal 1 is not doesn't have a Lindblad form, does it?
No, it's not Lindblad. It's not Lindblad, in fact, because you have this renormalization. It's non-linear. You have this renormalization here, which makes it non-linear. Lindbladian is linear. With the effective Hamiltonian, with non-remission effective Hamiltonian. So you can think. Sorry. If you renormalize it, it's completely positive. Because a state is positive for sure. Just start doubting whether it's completely positive. But it must be, because it is a result of a physical process, right? Any physical process is completely positive. You can think of it as a map. And this is the result of a measurement. No click is the result of a measurement. Right? So then it has to be completely positive. Shall I? Okay. So the model on which I'm applying this idea is the a key-type chain, which is basically a fermionic chain where you have this standard hopping term, and then you have also this weird superconductor term here. And on top of this, you have the chemical potential. So that's the pretty standard type of model in condensed matter. So then the measurement is encoded in fermion losses. So basically, you imagine having this type of Lindbladian on every single site. So this model is particularly nice because it gives you a completely linear, completely quadratic evolution. Again, in this model, this model is known to have entanglement phase transition, so measurement-induced phase transition, where you go in the no-click limit. So you know that here you have entanglement phase transition. And here, on the other hand, if you look at the full Lindbladian, you have a completely featureless steady state. Okay, so if you the full Lindbladian is completely boring. Now, the question is, what happens in between? And whether the question is whether there could be some interesting point in between, whether you can observe a transition between the left and the right side, or whether you have a sort of a crossing over.
What happens for mu greater than 1?
Sorry?
For mu greater than 1, what happens?
For mu greater than 1, what do you see?
Up to the first transition. There is a the first transition is
for gamma C.
Okay. For mu greater than, because of this value. Mu greater than 1, k is not possible because that would imply that your Fermi C, or basically there's nothing interesting happens if mu is greater than 1. Mu greater than 1, you cannot have any transitions.
Okay, just because the
It's like in the Ising model, because this can be mapped into the Ising model. You are in the situation where you are in a phase where your system is completely paramagnetic, so you cannot have a transition. So you are completely off. Okay. So it's not interesting. Yeah, it's outside of your regime of interest. As I was saying before, technically this model is nice because it gives you a dynamics which is quadratic. You see, if you have just term like this, you have only quadratic term in your evolution, which makes your evolution exactly solvable. So you can solve the evolution for any value of q, and the eigenstate, the steady state is always a Gaussian state in this case. And being a Gaussian state means that you can express all the features of your state in terms of this gamma thing, which is the covariance matrix. So everything is encoded there. So in a sense, very easy mathematically. Then there are a couple of quantities here that emerge if you look at the dynamics of your covariant matrix, which are basically simple matrices which are made out of the coefficient of your model. So nothing really interesting. There's no need to go into it. So the important point is looking at this equation, which is basically the equation of the covariance matrix of the steady state. Now you solve your problem, and from this you extract the correlation length of your system, basically, because the correlation matrix is giving you the information about the correlation length of your system. And then you go in Fourier transform, and you can sort of, even though it's analytically solvable to some extent, it's still quite difficult to find an exact value of the correlation length. What you can find is really an upper estimate of the correlation length, which you can analytically solve. And by doing by looking at the Fourier transform of the gamma matrix, you basically what you want to look in your gamma matrix, you want to look for every value of k, the quasi-momentum. You want to see whether they are real. They are in the real axis. They are zero. They are a point in which your gamma matrix looks singular. What does it mean, looks singular? That it jumps from one value to the other. And from these colors, you see that this jump here signals a jump in your correlation matrix. And if this jump happens for some imaginary value of k, from complex value of k, nothing really interesting happens. But if it happens at a real axis, it means that you have a real value of k for which you have a singularity, meaning you have a phase transition. Okay. So, and this is the case. For q equals to 1, your model has a jump for this special value of k. It goes from here to there. Now, if you analyze the same model in a situation where the q is less than 1, for example, 0.5, you see that here the transition becomes smooth across these values, meaning that the point in which you have a transition, the point that there are no real value in which you have a jump, and that gives you an estimate of your correlation length, which is the largest imaginary, the smallest imaginary value of k, where you have this type of jump, this singularity. So this means that for q equals to 1, your correlation length is infinite, basically means that you have a transition. For Q less than 1, you have a finite correlation length, which is telling you that you have no phase transition in this model. Basically, this is telling you that having Q less than 1 provide you a length scale, a minimum length scale, meaning that you have no infinite degrees of freedom, so that your transition doesn't happen at every degrees of freedom, at every distance on your model.
Okay, but these phase diagrams like that are for some gamma, for specific gamma.
These are for this is a specific value of gamma for the critical, for the, let's say, critical value of gamma. Yeah. What would be the critical value of gamma?
Okay. I'm sorry. Just, but if you don't look at the critical value of gamma,
You don't see this jump, sudden jump. Sorry. Okay, here we are. Yeah, so
it's completely fast. Let's say.
So it's a different, it becomes all blurred. You don't see this this singularity. Oh, maybe
No,
you
but
see singularity, but again, you may see some singularity, but not necessarily across, not in the real path for sure, which is the most important part.
Okay.
Most important part of the diagram. So yeah. So the yeah, so if you look for different value of Q, indeed, that's what you see. That you see that depending on the value of Q, you can also compute the inverse of the the correlation length, and you see that for the value of gamma, which is supposed to be the critical value of gamma, that's the one that I was mentioning. You see that the inverse of the correlation length is you can trace it analytically. This is the analytical value of the estimate that I was mentioning before. Is you see go all the way to 0, meaning that you have a diverging correlation length for Q that goes to 0. And of course, as you would expect, you have a finite correlation length for gamma, which is not in the critical. Is not critical. It's a finite, of course, correlation length in this case, which is expected. Okay. Now, the important figure, so that was the correlation length. An important figure of merit that people look is entanglement and negativity, so which tells you how entanglement is behaving in these systems. And you see that as you change the value of Q, again in the critical, for a critical parameter gamma, then you see that as you increase the size of your system for a value of Q which are less than 1, your entanglement negativity remains finite here. So at some point it grows and at some point it saturates. Whereas only for Q equal to 1, you get this continuous growing as you increase the system size. Meaning, so even for very small, even for very close value of Q, you have basically no signature of entanglement that grows like volume law. Meaning that you lose immediately observability of your phase transition as soon as you have something which is as soon as your detector is not efficient. Now, You can also use.
May I ask a question?
Yeah.
So basically, you're saying that for Q values different from 1, basically you have some sort of length scale
Exactly.
which
So
limits the growth of entanglement. So can you relate this length scale to Q in some way, like analytically?
yeah, it does. It is indeed. You can find an actual value. So the correlation length that you obtain for a given value of Q is the length scale that is giving you the sides beyond which you can, or under which you can say you have a sort of a phase transition. Okay.
Okay. And what would be the physical interpretation of that? So like, because in the end, right, this Q value measure like the quality of your detection. So how can it impact in the sense of introducing some sort of length scale in your system?
It's in a sense, it's if you want to make a parallel with temperature, right? For example, if you have an equilibrium phase transition, you say that temperature gives you a length scale beyond which you don't see quantum phase transition. So that's analog of that, because temperature is giving you, reducing the visibility of your phase transition because it's mixing up your quantum features. So in mixing up it's concealing, let's say, the quantum fluctuations. Similarly, here, the Q is giving you a length scale because it's smearing out the quantum fluctuations. Okay, because of you are basically mixing up. That's the same idea.
Okay,
so
thank you.
Result of some smearing happening at some along length scales.
Thanks.
So again, you can use other diagnostics like Burow's matrix, which is basically the quantum Fisher information, which is totally completely analog of the quantum, completely equivalent to quantum Fisher information. The Burow's matrix notoriously is nothing else than a measure of distance between states, next neighboring states. And notoriously, it's known, again, that there is this relation between quantum Fisher information and the Burow's metric. Again, this is a quantity which has been used in the last 20 years or so to characterize phase transition, because you know that the so-called Anderson orthogonality catastrophe tells you that whenever you have a ground state and you change it slightly because of some perturbation, then these two states becomes basically orthogonal. The overlap becomes small, and this overlap, the Burow's metric grows because of this feature. The Burow's matrix or the Fisher information grows with the size of the system, meaning that as soon as you make a small perturbation, two states becomes immediately very far away from each other. Now, that's generally true. That's always true for any condensed matter system. What is not generally true, what is more special is what happens when you have a quantum phase transition. Because in quantum phase transition, states become even more different from each other. And that encodes into the fact that the quantum Fisher information, or the Burow's matrix, doesn't just grow with the size of the system, but grows more extensively, let's say super extensively. So grows with a power which is not just 1, but is something like 1 plus x. So typically people say that quantum Fisher information, when grows with a system size more than extensively, people say that this is a signature of phase transition. And this can be observed also in this type of situation. And indeed, again, you can start asking yourself what happens to the quantum Fisher information if you have perfect detection And indeed, you see that if you have perfect detection, the feature information scales with the system size. It becomes larger and larger and larger, and scales with n squared in this type of system, meaning signaling the phase transition. On the other hand, if you have imperfect detection, that is no longer true, and indeed you can see that as soon as Q is not equal to 1, you have this feature information that scales only linearly with n. So basically, you are killing your phase transition. Okay, so and that was the first part. Probably I have like only. I'll be quick here. So the second part. Or if you want some questions, the first part.
Is this exponent
Universal? No.
Universal? Yeah. I mean, for
no, I wouldn't say it's a universal. Most of the, in this case, it might be universal. Generally, the way in which quantum feature information grows is dictated by universal exponents, generally. I haven't checked whether there is some universal property in this type of, related to the fact that you have a change of Q. So that's it.
Yeah. I guess one more question. Here you are always looking at the effective no-click limit, right? This is transition in the steady state of this no-click generator.
Right.
Do you expect it to hold if you actually have the measurement record and you don't have this deterministic?
Yeah, that's a good point. And it's actually, there are strong indications that you would, although you would need it's much more complicated to analyze because you have to keep track of many trajectories, average them if you want to do it numerically. If you don't want to do it numerically, you have to resort to field theory to try to solve the problem. And but there is some indication in some spatial model that is actually holding also in that type of scenario. And so I'll point you to some recent results.
So the Q in the link blood, that's link blood sort of link blood expression, cannot be mapped just as a rescaling of gamma, right?
Rescaling of the gamma, you mean the strength of the measurement? I don't think so, no, because there are two different physical effects, the Q and the gamma, because Q,
On average.
Essentially gamma provides you.
Physically, I understand.
No.
Sources are different.
Yeah.
But I don't know if on average, maybe you can rewrite it in such a way that, because at the end you look at average states.
Yes. For Q, yes. So you mean when you average everything out?
Yes.
There is some, in some sense, if you look at every single trajectory, so this setting that we are looking now, we are looking basically, we are concentrating at where Q is equal to 1, we are concentrating only on one trajectory, which is the no-click trajectory. Okay? So as he was saying before, you can analyze the standard way in which people analyze measurement-induced phase transition is by looking at the average over every single trajectory, even if you have Q different from 0, Q equals to 1. That's what we haven't done that because it's too complicated, let's say. So it's but in that type of framing, I think you can, in some sense, you can rescale. There is a sense in which you can rescale gamma by Q. There is something.
No, because in that picture, that this would be just going from the critical phase to the normal phase.
Yeah.
In a sense.
Yeah.
Which would make physical sense to me. We are doing Q, but what we are doing is just.
Yeah. In some sense that could be done. Yeah. But it's not straightforward. Okay, so in the second part, I sketch very briefly what is the second idea here. Here we are going from, instead of looking at monitoring every single site, we are just monitoring one single site. And the Hamiltonian, it's extremely simple, just a hopping Hamiltonian, Fermi hopping Hamiltonian. Nothing really interesting happens, apparently. So, and you look at the density, so local density, meaning is there or is not there Fermion. So then the standard way of describing this is by stochastic Schrödinger equation. So I don't need to go into technicalities because it's basically the similar machine of what I've just described in the first part. So what you expect in this type of scenario? But in this type of scenario, typically what you observe is a train of many clicks, and at some point, for some reason, you have some dark intervals. And then again, some trains of bunching of some click. And again, nothing happens for a while. So this is a typical pattern. It is actually not very new. If you do a standard measurement of spectroscopy measurement of a single atom, that's what you would expect, basically. Okay, so it's a typical pattern. But this type of pattern has an effect on what we see in our system. Indeed, if you look at if you plot here the waiting time between one click and the other, so you see that there are two types of behavior. One behavior in which all the waiting time are very close to each other, so basically are very small, and this corresponds to the bunching period. And then you have the dark intervals, which are extremely sparse. Extremely gives long waiting time. So this gives you a statistic which is called super Poissonian, and this is basically the Poissonian statistics there. Now, what has entanglement to do with this thing? So again, what the figure mate we want to look at the entanglement dynamics, how the entanglement changes this in time as due to one click as the effect of the observation. Okay, so between one click and the other, and you see this type of patterns. This is the entanglement, has how the entanglement changes in time. And you see, again, that the entanglement has this immediate change here. So it goes up and goes back again, up and back again after every single step. And then you see, again, the pattern of jump bunching and dark intervals here. Now, the interesting feature of this type of behavior is that if you look at how the entanglement changes in time, you see that initially, so start from the standard ground state of your system, and then you make a observation, keep on making observation, and you see that the average entanglement initially doesn't grow much, and then at some point it starts increasing and increase a lot, and it reaches a saturate at some value, which is very, very high, generally very high. It depends on the size of the system. Indeed, it gives you a volume law type of behavior. Okay, so and this volume law behavior of the entanglement is independent of the rate at which you measure. Okay, so it is not an entanglement phase transition, because in entanglement phase transition you have a transition in which depends on how strongly you measure. Here you have this volume law behavior, which is totally independent of gamma. Okay? It's there only because you measure.
Do you know how this relates to the? I don't know if you looked at this. If it's the same value as you would expect for a page curve in this U1. This sector of Gaussian U1 conserving states?
No, the answer is not. No, the answer is no, I don't know. But yeah, I know that there is this page analogy, page curve analogy, but I haven't gone into this. Yeah, that's a good point.
One thing, what is like this discontinuity along of the derivative?
There's no discontinuity. It's simply an artifact of the log-log behavior here.
Okay.
There's no. Yeah. So now, if you look at the, one may wonder why this happens. And if we look at another figure of merit, which is, for example, the free fermion energy, so the average of the Hamiltonian, you see that if you look at the entanglement entropy for a typical trajectory has this jump, and also the energy of the system has a jump whenever you have a jump here in the entanglement entropy. So there seems to be sort of a correlation between energy and entanglement. And indeed, if you look at there seems also to be a correlation between how long you are waiting, so how long you are waiting between one jump and the next one, and the increase of energy between one jump and the other. So there's this kind of positive correlation between the two things. It seems that the longer the time, the largest the increase of energy due to a jump, the longer is going to be the waiting time after the jump. Okay? So it's a strange type of correlation. It's not intuitive. So this is the waiting time that I was talking about. And the delta E is the change of energy that you observe after a jump. Now, you can make, as I said, you can look at the correlation between the change of entropy due to a jump and the change of energy due to a jump. And you see it's not obvious, but they are positively correlated. So there seems to be a strong change of entropy whenever you have a strong change of energy. So that's an important point. Now, indeed, if you divide the type of energy jump in those which do not provide strong energy change and those which provide small energy change, you see that there is also a correlation. Sorry, there is a correlation between the presence of a strong entropy and the presence of a strong energy. And now, an important point to make is, it seems that the increase of entropy, if you look at all these correlations, this increase of entropy that we observe seems to be correlated to the fact that you have a long waiting time between, so long interval, or if you want, long dark interval. So this seems that the longer the waiting time, the larger entanglement production you have. Okay, so the natural conclusion would be then who is responsible for this growth of entropy? Seems that the real responsible for this growth of entropy is the fact that you have this free evolution in between a jump. So it is the free evolution. So you have a jump, free evolution, a jump, and the growth of entanglement happens during the free evolution, not as the effect of the jump. Okay. So then one can try to guess and say, okay, then the jump has no role in this game, because it's the free evolution which is giving you this growth of entanglement. And so then the next step would be, okay, let's look at an evolution which is given just by the free evolution. And if you have only free evolution, this is a typical, for example, the average entanglement after one click and just free evolution. And you see this basically the entanglement doesn't grow at all, remains basically almost horizontal, and you have just a slight change of entanglement as you increase the size of your system, but nothing really serious. Basically, the entanglement remains basically bounded, doesn't grow with the size of the system. So the ultimate proof that is not just the free evolution which gives you this enormous growth of entanglement is if you look at this picture here. If you look at the change of entanglement, if you have just no jump, and you follow just the no-click Hermitian, no-click evolution, then you have this basically boring no growth of entanglement. If you look, for example, at free evolution and you sometimes put a Hermitian scattering, meaning that you replace your observation with just a scattering particle, Hermitian, in the single, you replace the single site with a standard potential, local potential, then you see again nothing really interesting here happening. You basically see a boring, flat evolution of the entanglement. Instead, if you add entanglement, as you add jump and free evolution, you have this amazing growth of entanglement that you see here. So the end of the story is, now I'll skip to the end. The end of the story is, in order to have a real growth evolution, sorry, I'll go just straight to the end. If you want this huge change of entanglement, you have to have both jumps and both free evolution. Is the alternation of these two effects which is providing this increase of entanglement in this system. And now one may wonder, this is the very last slide, one may wonder what happens if you go from a single monitoring site towards many monitoring sites. So basically, what happens is that in the single monitoring sites, you have this growth of entanglement, which is volume law here. Instead, if you slowly go, if you increase the sites in which you make monitoring, you go into, you can freeze your entanglement and you go back into the condition that we talk about in the first part, in which you basically are localize your system too much, and your entanglement doesn't have the room to increase too much. Okay, so in fact you see that in the extensive case, so an extensive number of monitoring sites, the entanglement doesn't grow much, remains basically flat here with increasing the system size. So, so these are basically take-home message. The first part I showed you the dependence on the monitoring efficiencies, and that basically they are detrimental for the observation of quantum phase transition or measurement-induced phase transition. And the second part, I showed you that a single site monitoring can be very effective in changing the entanglement property of your system, even as a very single site. That's, of course, has to do with the fact that the underlying Hamiltonian that you have is already a critical Hamiltonian, because having said that, the Fermi Hamiltonian, the standard Fermi Hamiltonian that I've described is already a critical Hamiltonian, because you basically, there's no gap in the phase diagram of your system. So basically, it is critical for every value of your parameters. So, and that's basically it. So if you have questions about the second part, or whatever. Go for it.
So here you're always starting, when you do this no click, you're doing, you're starting from the ground state with one applied jump.
Sorry?
What is the initial state of this no click and the emission scattering?
Is the ground state of the system, yeah. So
With some,
it's a free, is a closed system, so there's no in
I
blood.
mean, but you need to perturb it in some way, no, otherwise they know.
Yeah, you perturb it by measuring.
Okay, you measure once and then you evolve.
Yeah, you measure, you keep on measuring. You can do many different protocols. The standard protocol is you keep on measuring. If you measure once, nothing really interesting happens. So